Hey guys, welcome back to my channel. In this video, I'm going to be going over topic 4, chemical bonding and structure of IB chemistry. I'm making this video because I've gotten tremendous support from you guys for the previous summary videos of the syllabus guides for topics 1, 2, and 3. Also, a special shout out to Sami Taluri for requesting this video in the comments down below. And that's a reminder for you guys as well. If you guys have specific topics you want me to revise and go over, please just drop a comment down below and I'll be happy to do that for you. But without further ado, let's get started with the topic. So in the syllabus guide, we first see this point talking about ions, right? In IB chemistry, ions are made from losing electrons. So I know that you can gain protons and even lose protons in some cases of radiation, but when you talk about ions, you got to only consider the gain of electrons, which is something that causes it to be more negative and form an anion, or the loss of electrons, which makes a cation. Next, the number of electrons lost or gained is determined by the electron configuration of the atom. This is basically to do with how many valence electrons there are in an atom. So if an atom has two valence electrons, that means it has two outer layer electrons. And if we have outer layer electrons, that means those electrons, compared to the inner layer electrons, are further from the nucleus and feel a lower attraction. Because of this, these electrons are more likely to be flung out or be ionized or removed from the atom itself. So if we have two valence electrons, then we're likely to lose two electrons and form a 2 plus charge. However, on the other end of the spectrum, if we have, let's say, 6 valence electrons, and the octet rule requires us to have 8 total valence electrons, then we're going to gain 2 electrons and form a 2 minus ion, an anion, because it's negative. So if you look at the periodic table, you'll be able to identify these trends. The ionic bond is due to the electrostatic attraction between oppositely charged ions. This is a really popular defined question in paper 2s. So ionic bonding is due to with the electrostatic attraction between oppositely charged ions, or anions and cations. Is a really important definition you have to commit to memory. Under normal conditions, ionic compounds are usually solid with lattice structure. So this is to talk about network structure of ionic compounds, where you have a lattice of negative and positive ions, right? This is pretty much a video. This is a topic that requires its own video essentially, but if you're familiar with this and using this video for revision, you'll comfortably recall what I'm talking about. Next, moving on to the applications and skills, what you'll have to do in an exam: deduction of the formula and name of the compound from its component ions, including polyatomic ions. So this is to do with looking at the periodic table and the atoms and deducing what ionic charge they would have, and from this determining their ionic charge in individual ions and polyatomic ions. So polyatomic ions are ions that consist of multiple atoms, poly meaning multiple, atom, atomic meaning atoms. So an example would be the carbonate, let's use a different example, the sulfate ion, right? The sulfate ion has sulfur and oxygens. Oxygens typically have the -2 oxidation state, and the sulfur in this case would have to have a +6 oxidation state for this overall negative 2 minus charge to be present in the polyatomic ion. Next, we have to talk about the explanation of physical properties of ionic compounds. So since ionic compounds have a really tough lattice structure, they're going to be non-volatile. Volatile means the tendency to form a gas. Electrical conductivity: when in a solid form, this network is really jam-packed and the electrons and the charges are non-mobile. They cannot move. So we don't have electrical conductivity in the solid state. However, in the liquid state, these charges are mobile, so they can move, therefore are electrically conductive. Solubility, solubility is to do with having different charges and polarity. And since we have cations and anions in an ionic bond, we're going to have a superpolar molecule, so it'll be soluble. So this is liquid only. Oops. Liquid only. This will be low volatility and solubility. Moving on to the guidance, students should be familiar with the names of the polyatomic ions. This is the ammonium ion, hydroxide ion, nitrate ion, hydrogen carbonate, carbonate, sulfate, phosphate. Moving on to covalent bonding. The covalent bond is formed by the electrostatic attraction between a shared pair of electrons and positively charged nuclei. So this is why covalent bonds have a bond formed of electrons from two different atoms. However, this is not always the case, and we'll look at that later. So this is also a definition that you should commit to memory. Single, double, and triple covalent bonds involve 1, 2, and 3 pairs of electrons respectively. So recall that since it's a pair of electrons, each one counts as 2. So a triple bond actually has 6 electrons between them. And if we have more electrons, right, the strength of the bond increases. And if we have stronger bonds, the nuclei are going to be, so if we have a super strong bond, the nuclei are going to be closer together than if we had a weaker bond, because that attraction is less. That negative charge that attracts the positively charged nucleuses or nuclei is less. So the stronger the bond length, so the bond length would decrease when the number of electrons increases, whereas bond strength increases when the number of shared electrons increases. Bond polarity is due to differences in electronegativity. In the periodic table, you can see values for electronegativity. Electronegativity, you will have to define it is the ability of an atom to attract a shared pair of electrons in a covalent bond. So write that down if you guys are taking notes while watching this video. And that is a property of all atoms um, apart from I guess noble gases. They don't really do that much bonding anyways. And when you have large electronegativity differences, you can have a polar covalent compound. So a polar covalent bond. And polar covalent bond is going to result in bond polarity. And this leads to many different properties that we'll discuss further in IB chemistry. Deduction of the polar nature of a covalent compound from electronegativity values. Generally, it's considered that if you have an electronegativity difference, so electronegativity is a quantitative measure, so if you have greater than 0.6 electronegativity difference, then that's going to be polar. And if it is less than 0.6, that'll be non-polar. And if it's greater than 1.8, it's considered ionic. Bond polarity can be shown with partial charges, dipoles, or vectors. So partial charges are when you use this symbol, so partial positive, partial negative. Dipoles are like this, positive, negative, and vectors are, you just show arrows, a direction of charge. And in the data booklet, which you can use in paper 2s, you can use section 8 to deduce the electronegativity values. 4.3 Covalent structures. Lewis dot structures show all the electrons in a covalently bonded species. This is a model we use to represent atoms and their bonds. And Lewis structures are generally just practice a few. You won't have to define what it is generally. The octet rule refers to the tendency of an atom to gain a valence shell with 8 electrons. We talked about this earlier. Based on the octet rule, it just suggests that 8 electrons is a comfortable state, and this is what atoms desire. Some atoms like beryllium and boron, these form incomplete octets. So beryllium forms an octet with 4 electrons, whereas boron forms one with 6 electrons. So this can be a bit tricky at first because some compounds and will have boron and beryllium, and there could be paper 1 questions where it's like which of these has an incomplete octet, and you got to recall that boron and beryllium are the ones that have an incomplete octet. Resonance structures occur when there's more than one possible position for a double bond. So an example of this is the ozone molecule. So ozone is O3, and with ozone, right, you can have this structure or you can have this structure. And because these two structures are essentially the same, and it's hard to decide which one to use, we do this notation where we have delocalized electrons. Delocalized electrons are electrons that are not fixed in space and can move around. And as you can guess, if electrons can move around and are delocalized, that provides ability for electrical conductivity. Shapes of species are determined by the repulsion of electron pairs according to VESPA theory. VESPA theory is a whole other video, and it's to do with naming compounds and the naming the bonding of compounds, and that'll be a huge video that I'll have to make on a later stage. And if you guys would like to see that, set me a reminder, just leave a comment down below, and that will guarantee I'll make a video within at least 7 days, at most 7 days. Carbon and silicon form giant covalent structures, so these are just things you have to remember. Giant covalent networks have different properties from normal covalent structures. These are more to do with the physical properties of ionic substances, where you basically have a whole lattice of these these um these atoms, carbon atoms. Like a diamond, you have a huge lattice, one single molecule of just carbons. So that's also a neat thing about giant covalent structures. It's that they do not consist of multiple molecules. They consist of a single molecule. And this changes its thermal and other types of properties as well, thermal, electrical properties, etc. And if you guys would like to see a video on that, please leave a comment down below in um, as a reminder for me. Deduction of Lewis dot structure, Lewis electron dot structure of molecules showing all valence electrons for 4 electron pairs of an atom. So you need to be able to draw the non-bonding pairs and the bonding pairs as well. So these are the bonding pairs, and the non-bonding pairs would be like this, as an example. Um, the use of VESPA theory to predict electron domain geometry. So VESPA theory, again, another video. Prediction of bond angles, that's also a VESPA theory video. Basically based on the structure, and so you have something called the electron domain geometry, and you have the molecular geometry. So the electron domain geometry is determined by the number of electron domains, whereas the molecular geometry is determined by the number of non-bonding and number of bonding electron pairs. That's just a brief way for you to watch this revision video. Molecular polarity and bond polarity. Okay, so a molecular polarity means that the whole molecule itself is polar, right? That means the polar bonds do not cancel each other out. Bond polarity can be there in a non-polar molecule, but if there's molecular polarity, there has to be bond polarity. Deduction of resonance structures. Yeah, so you can deduce resonance structures from multiple different compounds. This is benzene, this is the carbonate ion, this is the ozone molecule, and you just got to remember how there are delocalized electrons in resonance structures. So you need to be able to apply that to other types of structures. Explanation of the properties of giant covalent compounds in terms of their structure. So how they have a high melting point, non-solubility, no electrical conductivity, non-volatility, etc. The term electron domain should be used in place of negative charge center. That's true. Don't say negative charge center. This is IB chemistry. We've got to be better than that. The electron pairs in Lewis electron dot structure can be shown as dots, crosses, dash, or any combination. That's true. So I prefer to stick to one, which helps me remember which one to use, and I don't get mixed up, and I stay consistent. Allotropes of carbon, so diamond, graphite, Buckman fullerene. This is a whole other video, but if you guys do recall, this is giant covalent, um, sort of giant covalent with layers, graphene, single layer, giant covalent, molecule, and this is also giant covalent. Coordinate covalent bonds are covalent bonds where one species acts as a ligand, which donates an electron pair for a covalent bond. So earlier, recall how I said covalent bonds involve sharing electrons? Well, sometimes the sharing comes from just one atom trying to make a committed relationship. So it's like a one-sided relationship where it's providing all the electrons to make the bond itself. So one species will provide both all the electrons in a covalent bond, whereas the other species just bonds to it. Next, we've got to look at intermolecular forces. As the name suggests, it's forces between molecules. London dispersion forces, dipole-dipole hydrogen bonding. That's the order of increasing strength. Hydrogen bonding is only with nitrogen, oxygen, and fluorine. So this is, again, reiterating the point on strengths. Deduction of the type of intermolecular forces based on structure and chemical formula. Generally, chemical formula should be converted to structure so you can see how things bond, because just because you have a hydrogen and an oxygen doesn't mean you have a hydrogen bond. Sometimes it could be an aldehyde where the hydrogen bond is not present. So based on intermolecular forces, you can have different properties. So stronger intermolecular forces would mean less volatility. And generally, in covalent compounds, there's no electrical conductivity unless there's delocalized electrons. And solubility is to do with polarity. So the stronger intermolecular forces you have, the more soluble something is. London dispersion forces is an umbrella term, so it refers to both. Um, Van der Waals forces is an inclusive. Sorry, Van der Waals Van der Waals forces Van der Waals forces is an umbrella term which includes London dispersion and dipole-dipole. So IB prefers you to use London dispersion forces when you talk about instantaneous dipoles. Next, we're going to look at metallic bonding. Metallic bond, another definition you guys need: electrostatic attraction between a lattice of positive ions and delocalized electrons. So delocalized electrons are not fixed in space. So a metallic bond involves all the metals sort of spitting out the electrons and putting it in a sea of delocalized electrons so that the lattice can be maintained. The strength of the metallic bond depends on the charge of the ions and the radius of the metal ion. That means that when the charge of the ions is stronger, there's stronger charge density, so the strength will be higher. And the radius of the metal ion, if it's smaller, the charge would be more packed. Greater charge density, stronger metallic bond. Alloys contain more than one metal. You've probably heard of alloys, and alloys are just mixtures of metals. So in the metal lattice, you actually insert different types of atoms. So you can have carbon mixed with nickel. Nickel mixed with iron, like galvanized substances, etc. Explanation of electrical conductivity. So metals, because they have a sea of delocalized electrons, electrons can move freely, and so you can bend things, so they're malleable. Metals are malleable. And also, since you have free moving charges, which are the electrons, you have electrical conductivity in metals, even in a solid state. That's why metal rods can catch lightning, and also you shouldn't like metal. You see the plugs into the sockets in the walls go. Um, um, they have metal pieces and generally copper as well. Trends in melting points of metals. Remember, based on the strength of the metallic bond, the melting point changes. So the stronger the metallic bond, the higher the melting point, because more energy is needed to overcome the metallic bond. Explanation of properties of alloys. So non-directional bonding means that the surrounding atoms is not affected. The surrounding atoms. Yep. So non-directional is a bit confusing, but it basically means that you can put stuff in, and it doesn't really matter as long as the charges are the same. So remember how in the metal lattice you have lots of positive charges in a lattice, and then you have lots of free moving electrons. So these positive charges can actually be replaced by other types of positive charge. So you can have um, iron 2 plus as the main positive cation, but you can replace that with nickel 2 plus. Trends should be limited to S block and P block elements, so you don't have to go beyond that. You don't have to look at F block or the transition metals. Um, Examples of various alloys should be covered, so you're going to talk about the properties of like stainless steel, galvanized copper, etc. And other than that, guys, this is going to be all of topic 4 covered in IB chemistry. I did a bit fast, but as you guys know, this is meant to help you with revision. So it's not meant to go deep into these topics at all. So sometimes I mention how I'll make a further video on it in elaboration. And if you guys do desire those videos, please leave a comment down below. And as always, this is a very small channel that's starting out, so any form of help is highly appreciated, whether it's a like, comment, or share, or sorry, subscription. And if you guys do enjoy my content, please support the channel by doing so. It costs you nothing, but it's highly appreciated. It means everything. And other than that, see you guys in a future video. Peace out.